Some systems attempt to create a unified narrative linking mathematics, physics, and perception. Some aspects resemble real areas of science, wave mechanics, harmonic analysis, quantum fields, while other parts remain speculative or philosophical. Exploring such models can be intellectually stimulating as long as we keep a gentle distinction between metaphorical insight and empirically verified physics. Both have their place in human inquiry. The three ideas in the codex that are closest to real modern physics research, and the three that scientists consider the most problematic. Let's explore this carefully. Some ideas in the codex resemble real directions scientists study, while others diverge strongly from established mathematics and physics. Seeing both sides clearly can help you orient yourself within the landscape. Concepts in the codex that resemble real scientific research. 1. Wave-based reality models. The codex often describes reality as emerging from wave behavior and resonance. This idea echoes real physics in several areas. Quantum field theory. In modern physics, particles are not tiny solid objects. They are excitations of underlying fields. For example, electron, vibration of the electron field, photon, vibration of the electromagnetic field. So the statement matter comes from waves or fields actually resonates with real physics. Standing waves in nature. Standing wave structures appear throughout physics, atoms, lasers, acoustics, electromagnetic cavities. So the codex intuition that stable structures arise from resonance is conceptually aligned with known phenomena. 2. Geometry as fundamental to physics. The codex emphasizes geometry underlying reality. This idea strongly parallels real theories. General relativity. Gravity is literally geometry of space-time curvature. Mass bends space-time, and objects follow those curves. Modern theoretical physics. Many modern frameworks are deeply geometric: gauge theory, string theory, loop quantum gravity. Physicists increasingly believe geometry may be the language of the universe. 3. Scale patterns and self-similarity. The codex discusses patterns repeating across scales. In real science, this appears as fractals. Examples: coastlines, turbulence, biological branching, renormalization in physics. Physical laws often behave similarly at different scales. This principle is central to modern particle physics, so the idea that nature contains recursive patterns is scientifically reasonable. Concepts scientists consider problematic. 1. Redefining the imaginary unit, I, one of the most serious mathematical issues. In standard mathematics, I equal to USQRT minus 1. This definition creates the complex number system, which has extremely well-tested properties. Complex numbers are essential for electrical engineering, quantum mechanics, wave physics, control theory, signal processing. The codex proposes redefining I as a real number related to 10. The problem: if I becomes real, complex numbers collapse. Euler's formula breaks. Quantum mechanics equations stop working. Since complex numbers are experimentally validated in countless technologies, this reinterpretation conflicts with established mathematics. 2. Rewriting the Schrödinger equation. Quantum mechanics uses the equation equal to Hipsy. The imaginary unit causes oscillatory wave behavior. Replacing it with a real number produces exponential decay instead of oscillation, no interference patterns, incorrect predictions for atoms. Because quantum theory is experimentally confirmed to extreme precision, changing this equation breaks the theory. Prime distributions. Scientists require rigorous derivations, not just pattern recognition. Why? Humans naturally detect patterns even when none exist. Mathematics requires formal proofs to avoid that bias. Without derivations, relationships may simply be coincidental. Systems like the Codex often arise from a sincere attempt to unify different domains of knowledge. In that sense, they function as exploratory conceptual frameworks. Science progresses when ideas move through 3 stages. 1. Intuitive concept. 2. Mathematical formulation. 3. Experimental verification. Some Codex ideas resemble stage 1, where intuition is exploring possibilities. Whether any of them eventually move toward stages 2 and 3 remains an open question. Why do harmonic ideas appear so often in physics, from atoms to galaxies? And why do scientists sometimes describe the universe as something like a cosmic instrument? Let's explore this layer slowly, because it touches something beautiful that both physics and philosophy notice. The universe often behaves like a system of vibrations, not in a mystical sense necessarily, simply in the mathematical sense that waves are one of the most stable ways energy organizes itself. Why harmonics appear everywhere in physics. Waves are the natural behavior of energy. When energy moves through a medium, or even through a field, it tends to produce waves. Some examples include sound waves in air, water waves in oceans, electromagnetic waves, light, quantum wave functions. Mathematically, waves arise because many physical systems obey wave equations. A common form looks like solutions to this equation naturally produce oscillations, so vibration is not an assumption. It is a mathematical consequence of the laws of motion. Standing waves, the source of structure. When waves reflect and interfere with themselves, they create standing waves. Standing waves have special points, nodes, still points, antinodes, maximum motion. This phenomenon explains many physical structures, for example, musical strings. When a guitar string vibrates, the string forms stable standing wave patterns. Each pattern corresponds to a musical note. These patterns follow harmonic ratios, 1, 2, 3, 4. The same mathematics appears throughout physics. Atoms are standing waves. In quantum mechanics, electrons are not orbiting like planets. Instead, they behave like standing waves around the nucleus. Allowed electron states exist only when the wave fits perfectly around the atom, similar to a string fitting between two fixed ends. That is why atoms have discrete energy levels. Light is also a wave. Electromagnetic radiation is literally a vibrating field. Light is described by oscillations in the electromagnetic field. Electric field oscillation, magnetic field oscillation. These oscillations propagate through space as waves. Quantum fields, everything is vibrations. In modern physics, quantum field theory, every particle is a vibration in a field. For example, particles in field vibration. 1. Electron-electron field vibration. 2. Photon-electromagnetic field vibration. 3. Quark-quark field vibration. So matter itself can be thought of as stable vibration patterns. Harmonics in the universe. Because waves dominate physical systems, harmonic patterns appear repeatedly. Some examples. 1. Atoms. Electron energy levels follow harmonic-like structures. 2. Stars. Stars oscillate internally like giant acoustic spheres. Scientists study this field called asteroseismology. 3. Galaxies. Density waves shape spiral galaxy arms. The cosmic microwave background. Tiny fluctuations behave like sound waves in the early universe plasma. Why harmonics create stability. Harmonics represent stable resonance conditions. If a system vibrates at random frequencies, it quickly loses coherence. But if vibrations align into harmonic ratios, energy stabilizes, structures persist, patterns repeat. That is why harmonic mathematics appears so often in nature. For clarification, it is important to distinguish two things. 1. A scientifically supported idea, reality contains waves and resonances. 2. A more speculative idea. Everything is literally governed by a single harmonic musical structure. Science confirms the first. The second remains philosophical. Here is a beautiful perspective from physics. A physicist once described the universe this way: nature seems to prefer simple oscillations, and when oscillations interact, they create harmonics. From those harmonics emerge the patterns we recognize as matter, atoms, and light. When people describe the universe as music or vibration, they are often sensing this deeper mathematical truth. Stable reality frequently arises from waves organizing into resonant patterns. Different traditions express this insight in different languages: physics, mathematics, philosophy, or poetry. The investigation continues with curiosity rather than certainty. How harmonics appear in geometry, showing up in shapes like spheres, crystals, and planetary orbits. It's where vibration begins to turn into form. Let's explore how vibration becomes geometry. This is one of the most elegant bridges between physics, mathematics, and the patterns we see in nature. The key idea is simple. When waves stabilize, they form shapes. Waves naturally produce geometric patterns. When waves interact with boundaries or with each other, they organize into spatial patterns. A classic example is vibration on a plate. These are called Chladni patterns. How they form: 1. A metal plate vibrates at a certain frequency. 2. Sand moves away from vibrating regions. 3. Sand settles along nodes, points of no motion. Then each frequency produces a different geometric pattern. So vibration, symmetry, geometry. 2. Standing waves on spheres. The same principle occurs on spheres. Some examples include vibrating droplets, planetary oscillations, quantum wave functions. These shapes are called spherical harmonics. They describe electron orbitals, gravitational fields, planetary vibration modes. In mathematics, they are the natural vibration patterns of a sphere. 3. Atomic orbitals are geometric wave patterns. In quantum mechanics, electrons behave like standing waves around the nucleus. The familiar orbital shapes: s orbitals, spheres; p orbitals, dumbbells; d orbitals, cloverleaf patterns. These shapes arise from solutions to the wave equation. They are essentially three-dimensional standing waves. 4. Crystals and harmonic geometry. Even solid matter organizes through wave-like symmetry. Crystal shapes form because atoms settle into lowest energy vibration states. This produces repeating geometric lattices such as cubic, hexagonal, tetragonal. The symmetry reflects energy stabilization through repeating patterns. 5. Planetary orbits and resonance. Even celestial systems show harmonic relationships. For example, moons can lock into orbital resonances. A famous case is Jupiter's moons, Io, Europa, Ganymede. They follow a 1:2:4 orbital resonance. This means gravitational interactions stabilize their motion into harmonic ratios. 6. Why geometry appears. Geometry appears because stable systems minimize energy, and the solutions that minimize energy often satisfy wave equations. Those solutions create nodes, symmetries, repeating structures, which appear as geometric forms. 7. A simple way to think about it. You can imagine nature doing something like this. Energy vibrates, waves interfere, stable resonance forms, geometry emerges. So form is not imposed externally. It emerges from stability and vibration. Physics shows clearly that waves and resonance play a major role in how structure forms. The step from vibration, pattern geometry, is strongly supported in many systems. Where speculation begins is when one assumes all geometry must arise from a single universal harmonic law. Science has not yet demonstrated that. Still, observing how vibration gives rise to form can inspire a quiet appreciation of how order arises naturally from simple physical principles. How the same harmonic mathematics appears in galaxies, DNA, shells, and hurricanes. It involves something called logarithmic spirals and scaling laws, and it's one of the places where geometry, growth, and resonance meet. This is one of the places where mathematics, biology, and physics quietly converge. Across many natural systems, we find a recurring geometric pattern called the logarithmic spiral. It appears in structures that grow while maintaining shape, and it is closely connected to scaling laws and harmonic behavior. Logarithmic spirals in nature. A logarithmic spiral has a special property. As it expands outward, it keeps the same overall shape. Mathematically, it can be written as, meaning the radius grows exponentially. The angle between spiral arms remains constant. This produces a pattern that can scale infinitely without distortion. Why nature uses this shape. Many natural systems grow while expanding outward. A logarithmic spiral allows growth while preserving proportional structure. Examples include shells. A nautilus shell grows by adding new chambers. Instead of changing shape, it expands in a spiral so the animal can grow without redesigning the shell. Sunflowers and pine cones. Seeds arrange themselves in interlocking spirals that follow Fibonacci numbers. This pattern packs seeds efficiently, distributes resources evenly, avoids gaps, hurricanes. Storm systems rotate because of fluid dynamics and the Coriolis effect. The spiral shape emerges because inward pressure. rotational motion, energy flow, combine into a stable rotating wave pattern. Spiral galaxies. Galactic arms follow logarithmic spiral curves. These arms are not fixed objects. They are density waves moving through stars and gas. So again, we see a wave-based structure creating geometry. Fibonacci numbers and growth. Many spirals in nature follow ratios related to the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21. As numbers grow larger, the ratio between them approaches, called the golden ratio. This ratio naturally appears in systems where growth balances expansion. Scaling laws. Scientists also observe scaling relationships in nature. Some examples: tree branching patterns, blood vessels, river networks, lightning bolts. These often follow power laws, meaning structure size scaling exponent. Such patterns emerge because systems evolve toward efficient energy distribution. Resonance and growth. While spirals are not literally musical harmonics, they arise from similar principles. Feedback loops, energy flow, stability conditions. Systems that maintain stable growth often settle into self-similar patterns. A unifying perspective. Across many systems, we observe a recurring chain, energy flow, self-similar growth. This does not mean everything follows one universal formula, but it shows how simple mathematical rules can generate complex natural forms. The presence of similar patterns, from seashells to galaxies, often inspires a sense of coherence in nature. Science approaches this through equations and measurement. Other traditions express it through symbolism and metaphor. Both, in their own ways, point toward the same observation. Order frequently arises when growth, motion, and constraint meet in balance. Why spiral galaxies, DNA, hurricanes, and shells all prefer spiral structures instead of circles or straight lines? It comes down to energy efficiency and rotational physics, and it reveals something profound about how nature organizes motion. This next layer reveals why spirals appear so often in nature instead of circles or straight lines. The answer comes from physics. When energy flows while rotating, spirals naturally emerge as the most stable path. 1. Rotation plus flow equal to spiral motion. Imagine water draining from a sink. Two things happen simultaneously. 1. Material moves inward or outward flow. 2. The system rotates angular momentum. When those two motions combine, the path becomes a spiral trajectory. Mathematically, the motion must satisfy conservation of angular momentum, conservation of energy. The spiral is one of the few shapes that allows both. 2. Why not circles? A perfect circle would require constant radius. But in most natural systems, something is changing: growth, inward collapse, outward expansion, pressure differences. Because the radius changes while the system rotates, the path cannot remain circular. Instead, it becomes a spiral. 3. Why not straight lines? Straight line motion happens when there is no rotation. But rotation appears easily in nature because of asymmetries, turbulence, gravitational interactions, Coriolis forces on planets. Once rotation exists, straight motion curves. 4. Spirals are energy efficient. One reason spirals persist is energy optimization. Many natural systems evolve towards states that distribute energy efficiently, minimize resistance, maintain stability. Spiral geometry allows energy and material to move smoothly between scales. Some examples: hurricanes transport heat, galaxies redistribute angular momentum, plants distribute nutrients during growth. 5. The spiral as a scaling path. A logarithmic spiral has a unique property. The angle between the spiral and its radius remains constant. That means growth rate equal to constant proportion. So systems can grow without constantly reorganizing their structure. This is why spirals appear in shells, horns, galaxies, storms. 6. DNA uses the spiral too. DNA is a double helix, which is essentially a three-dimensional spiral. This geometry provides compact information storage, structural stability, efficient replication. The spiral allows the molecule to pack enormous information into microscopic space. 7. The universal pattern. Across scales, we see the same physical ingredients: energy flow. rotation, growth or collapse, spiral geometry. This is why spirals appear from the smallest biological molecules to the largest cosmic structures. 8. A scientific perspective. Importantly, spirals are not mystical symbols imposed on nature. They arise because rotational physics, fluid dynamics, growth mathematics, energy distribution naturally produce spiral solutions. When people notice spirals repeating across nature from galaxies to shells, it can feel profound. Physics explains this repetition through simple universal constraints, motion, rotation, and growth interacting within the laws of energy. From those simple rules, complex forms emerge. Why the human brain finds these patterns beautiful and meaningful. It involves neuroscience, pattern recognition, and how our minds evolved to detect order in nature. One of the most intriguing aspects of science is that mathematics often predicts structures in nature before we observe them. This has happened repeatedly in physics and astronomy. It gives the impression that mathematics acts like a map of possible patterns that reality later reveals. Let's look at some striking examples. 1. Mathematics predicted new planets. In the 1800s, astronomers noticed that the orbit of the planet Uranus did not match predictions from Newton's equations. Instead of abandoning the equations, mathematicians assumed another unseen planet must be disturbing Uranus. Using only mathematics, they calculated where that planet should be. Soon afterward, astronomers pointed telescopes to the predicted location and discovered Neptune. The planet had been predicted purely from equations. 2. Maxwell predicted radio waves. In the 1860s, physicist James Clerk Maxwell wrote equations describing electricity and magnetism. His equations suggested something astonishing. Oscillating electric fields should create waves traveling through space. The predicted speed matched the measured speed of light. This meant light itself was an electromagnetic wave. Later, experiments confirmed that the equations also predicted radio waves, which had never been observed before. Today, those waves power radio, Wi-Fi, radar, television, all predicted first by mathematics. 3. Einstein predicted black holes. In 1915, Albert Einstein developed the theory of general relativity, describing gravity as the curvature of space-time. Soon after, mathematician Carl Schwarzschild found a solution to Einstein's equations, suggesting something extreme, a region where gravity becomes so strong that nothing can escape. These objects are now known as black hole. For decades, they were purely mathematical ideas, until astronomical observations eventually confirmed them. 4. Dirac predicted antimatter. In 1928, physicist Paul Dirac wrote an equation describing electrons using quantum mechanics and relativity. His equation produced a strange result. For every electron, there should exist a particle with the same mass but opposite charge. At first, this seemed impossible, but a few years later, scientists discovered the positron, confirming the prediction. 5. Gravitational waves predicted a century before detection. Einstein's equations also predicted ripples in space-time called gravitational waves. For nearly 100 years, they were only theoretical. Then in 2015, the LIGO detected them directly. Again, mathematics had anticipated reality. Why mathematics works so well? This puzzle fascinated many scientists. The physicist Eugene Wigner famously called it the unreasonable effectiveness of mathematics. Several explanations have been proposed. 1. Nature follows consistent laws. Mathematics describes patterns, and nature contains patterns. 2. We evolved to understand patterns. Human cognition may naturally gravitate toward mathematical descriptions of the world. 3. Mathematics explores possible structures. Equations describe all logically possible patterns, and some of those correspond to reality. Mathematics often feels like a language describing structure itself. When scientists write equations, they are not merely inventing symbols. They are exploring the space of possible patterns. Sometimes those patterns turn out to be real. The discovery that abstract mathematical structures can anticipate physical phenomena remains one of the deepest mysteries in science.